Okay, let's continue our seminar, and our next speaker is Oleg Chalykh from Leeds about elliptic reflection groups and Seiberg Witten integrable systems.
Okay, thanks very much. First, thanks very much for the invitation. It's really nice to be here, and I will speak about our joint work with Philip Argyres from Cincinnati and Yongchao Lü, who is in Seoul. And so we have two papers on this subject on arXiv, and more are coming. Why it doesn't turn right? Ah, yeah, okay, yeah, and more coming. Okay, so this is a collaboration which started incidentally when we both, me and Yongchao, were at a workshop, and just in the conversation, I brought up this this topic of this Calogero Moser type integrable systems related to complex reflection groups, and he suggested that they could be related to physics, and that's this is the byproduct of that idea. And so let me just tell you the plan of the talk. So I will give some motivation. Then I will talk about global theoretic algebras, which underlie the construction of these integrable systems. And then mostly I will talk about rank 1 case, the simplest possible case, where already you see some interesting geometry and interesting features. So the main underlying geometric object here will be elliptic curve with symmetries. And there are interesting Lux matrices appearing here with a nice duality. And this will lead us to geometry related to certain elliptic pencils, which should be closely related to some pencils appearing in the theory of discrete Penlever equations. And then, if time permits, I will say something about quantization of spectral curves towards the end. Okay, so let me start with the motivation. So the motivation comes from physics, and it all started with the observation by Seiberg and Witten, saying that every four-dimensional n equals 2 supersymmetric quantum field theory has an underlying complex integrable system, which can be observed at low energies. And so let me first tell you a little bit about what is a complex integrable system. So this is unlike the usual real integrable system, this is a system on the complex manifold. And so the Hamiltonians are complex valued functions, and you're supposed to have n of them, and you have a holomorphic Poisson structure. So the Hamiltonians are in involution. And this is not enough to call this integrable system. In the real case, there is a well-known Liouville-Arnold theorem, which tells you that that's all you need. But here you need to require separately that all the fibers of this map pi are abelian tori, and the dynamics of your Hamiltonian dynamics for each of the Hamiltonians is linearizable on these torus. So the dynamic is linear along fibers. And this is by no means automatic. So for example, you can think of integrable system with just 1 degree of freedom. So level sets of the Hamiltonian are just complex curve in 2 dimensions. And of course, you don't expect it to have genus 1 necessarily. So what you require to have to be elliptic curve in this case, which is a much stronger requirement. In the real case, the level surface, if they're compact, they're just circles, and you don't need to do anything else. But here, it's a stronger requirement. And I'm a little bit imprecise here, because typically imagine that if your manifold was for example, a fine algebraic manifold, then the level surfaces of your integrals will never be compact. So when I say that they are abelian tori, I mean that they naturally compactify to abelian tori. So that's the usual situation. And then important physics information is captured by typically what you have in addition to that is the following ingredients. So you have actually a family of curves parameterized by the same parameter z, and these curves. So this is n-parametric family of curves. You want them to have genus n, and then the fibration in good circumstances actually is the fibers are Jacobians of these curves. Okay, and then another important ingredient is this Seiberg Witten differential. Yes, somehow. Seiberg Witten differential lambda, which is a certain meromorphic one form on these curves with special properties and containing important information about the physics. Okay, so that's the background. So since according to Seiberg Witten, every 4D n equals 2 SQFT has underlying complex integral systems. So it means that there are lots and lots of these integrable systems, much more than you normally learn when you study integrable systems. And so it started actually a hunt for unfortunately there is no clear algorithm how to find out which integrable system underlines your SQFT. So sometimes it requires guesswork. Typically, you compare information from integrable system side to information you expect in physics, and this allows you to match these two sides. And there are two main overlapping sources of integrable systems which have been already identified as Seiberg Witten integrable systems. So one source is n-particle integrable systems like Todd and spin chains and elliptic Calogero Moser system in particular. And another source is Hitchin systems on Riemann surfaces, typically punctured Riemann surfaces. And our proposal is that complex crystallographic Calogero Moser systems actually are a good source of Seiberg Witten integrable systems. Okay, so I will talk about this in more detail next. But let me just mention that if you're if the Calogero Moser system is related to a real crystallographic group, then this has been known already. So going back to Danagi and Witten, they identified the Calogero Moser system, elliptic Calogero Moser system in type A as a particular Seiberg Witten integrable system of supersymmetric Mills theories with SUN gauge group. And then Hocker and Fong extended this to other Calogero Moser system related to other root systems. And so our proposal is to go beyond, to go these complex crystallographic groups. And the underlying structure here is the Cherednik algebra, sometimes called global Cherednik algebras. So this is due to Etingof, who introduced them in the following context. Suppose you have a finite group acting on a smooth complex manifold of dimension n. Then he constructed Cherednik algebra H for such a pair as a deformation of the following sheaf of algebras. So you take structural sheaf of the cotangent bundle to X and then cross product with group W, and this has a deformation with maybe several parameters. So C here indicates the set of parameters, deformation parameters, and similarly, there is a spherical subalgebra sitting inside this Cherednik algebra, which is a deformation of the structure of the structure sheaf on the this orbifold, the quotient of the cotangent bundle by W. And there are also quantum versions of these algebras, which will be useful when you consider quantization. Okay, so that's the general geometric background. So there is this family of algebras. These are sheaves of algebras. And maybe just to give some flavor, and it will be useful also to look at baby example. The simplest maybe example of Cherednik algebra is when you take X to be just a fine line, complex line with action by roots of unity. W is a cyclic group of order M acting on the cotangent. So cotangent bundle to X is just, you can think of it as C2, and the roots of unity act by the following matrices. So this is symplectic action, and you look at the functions on this orbifold. So this is C2 over Zm. It's known as cyclic singularity or singularity of type A. And if you think of which polynomials in two variables are invariant under such action, you can work out that you need three generators, and they're related by this relation. So this is well-known cyclic singularity of type AM minus 1. And deformation of this singularity, there is a natural Poisson deformation of this singularity if you replace this monomial V2M by arbitrary polynomial of degree n. And then you can actually rescale generators to make this polynomial monic. And by shifting the variables, the generator V, you can also achieve that the next coefficient vanishes. So altogether, you have M-1 essential parameters of deformation. And that's the spherical subalgebra of that Cherednik algebra in this case. Okay, so that's a deformation of type A singularity. And this deformation geometrically, in the simplest case, when M is 2, you can think of that as having a cone singularity, and deformation is just replacing it with hyperboloid. Okay, right, okay. So for this integrable system, you need to take X to be special, namely it has to be, it needs to be abelian variety, so quotient of a fine space by a lattice of full rank to n, and W will be a finite group acting on X, which means that it's a subgroup of GLN preserving this lattice lambda, and it's enough for us to restrict to the case when W is a complex reflection group. Because in fact, all the deformations I talked about in the previous slide, they only appear when you have pseudo reflections in your group. So it's natural to just restrict to this case. So complex reflection group, it's if you know about Coxeter groups, then complex reflection group is a generalization when you allow reflections of higher order than 2. And there is a full classification of finite group W like that. But then if you cross them with the lattice, you obtain what is called crystallographic complex reflection group, or in my title for the talk, it was elliptic crystallographic, elliptic complex reflection group. So that's another name. So this is actually an infinite group and still generated by reflections. And such groups fully classified by Popov. There is a full list, and there is a theorem by Etingof, Felder, and Veselov, which, yeah. Well, it's kind of elliptic version because lambda is a lattice of full rank, like 2n, right? So on the next slide, I will see how it looks. Yeah, so it's sort of elliptization in a way. Yes, they're allowed. They're allowed. Yes. So this is complex reflection group rather than just real Coxeter group. Yes. Okay, and so for such X, you have quadratic algebra and spherical subalgebra. These are sheaves. So it means that if you choose different open sets, you get algebras of local sections. And if you increase your open set, the algebra of global sections becomes smaller. So you don't, in general, you might not get any global sections at all. So what happens here is that the algebra of global sections actually for this sheaf of algebra is a polynomial ring on n generators and which are Poisson commute. And the same is true at the quantum level. The algebra of global section of the quantum quadratic algebra would be a polynomial ring on n generators. And this defines an integrable system on this abelian variety. So this is what I will refer to as this complex crystallographic Calogero Moser system. Okay, so these systems are very complicated in general, so there is no nice way of writing Hamiltonians. The orders, so if you think of these global sections, H1 up to Hn, they are polynomial in momenta, but the degrees of these polynomials are the degrees of polynomial invariance of your group W, so they could be very high, of very high degree. So and therefore, if you read, for example, the paper where this integrable system were constructed, there is a footnote, apologetic footnote saying that, well, probably these systems don't have physical meaning because the Hamiltonians are of high order and complicated. But it was a surprise that actually they are very much physically relevant, at least in the cases we already know. Yes, so here is coming back to what Bart asked. So if you have a usual real crystallographic group, then what you can do, you can consider this abelian variety when you take root lattice and then double it using complex number tau, and that's in this case the corresponding integrable system is exactly this elliptic Calogero Moser integrable system of type W. Here is a formula for the quadratic Hamiltonian in type A, when you have this system of n particles on the line interacting with this elliptic potential. Okay, and so this was known to be, as I already mentioned, from 90s, it was known to be a particular Seiberg Witten integrable system. And so what happens if you go beyond real crystallographic case? So that's our project, and so far we know the answer in the case when you take X to be a product of n copies of elliptic curve, but elliptic curve you assume that has a symmetry, and so so elliptic curve with symmetry of a cyclic group of order M acting on E, of course, due to well-known elementary geometric result, these groups of unity, they act as rotations, and the lattice cannot have rotations unless they have order 2, 3, 4, or 6. And so these are the possibilities. And so the group, the complex crystallographic group associated to this case, well, the finite group generated by reflections in this case will be just this, what is sometimes called the wreath product of Sn with Zn, or semi-direct product of like that. So here the roots of unity act on each copy of elliptic curve, and symmetric group just interchanges the factors. Okay, so in this case, it turns out that when M is 2, this integrable system is behind certain 4D n equals 2 superconformal field theory with gauge group USP2n. This is quaternionic kind of analog of unitary group, special unitary group. While for M equals 3, 4, and 6, the corresponding physical theories are so-called Minahan-Nemeshansky superconformal field theories of type E6, E7, E8. of rank n. Okay, and a nice feature of this correspondence is that deformation parameters which we have for geodetic algebra, they match very nicely, just one-to-one, to the physics parameters, mass parameters of SQFT. Okay, so that's what we know so far. And next, I will talk just about rank 1 case. So there will be just one elliptic curve with a symmetry. And in this case, this will be theory of rank 1. Okay, and and by the way, maybe going back to that case, I'm by no means an expert in this quantum field theories, but what my collaborators, what I learned from them, that, for example, these theories they don't have a Lagrangian description, so obtaining some information about them in this way might be useful because other conventional tools are not available. And okay, so rank 1 case, you have elliptic curve with a symmetry, the m is 2, 3, 4, and 6. And I will think of the cotangent bundle to elliptic curve with canonical coordinates p and q. And the group acts, so q will be uniformizing coordinates on my elliptic curve. P is in the tangent direction. And the group acts again as before. You can think of the matrices like that. And if M is 2, then you can choose any elliptic curve because it has Z2 symmetry. Q goes to negative Q. But if you have M equals 3 or 6, you need hexagonal lattice. And for M equals 4, you need square lattice. So this you lose this freedom. You have just specific modular parameter in those cases. Okay, and so here are some pictures. So I would like to tell you that there is some kind of link, maybe non-obvious link between these elliptic curves with symmetries and the affine Dynkin diagrams of type D4, E6, E7, E8. At least in simple terms, it can be explained as follows. So if you have, these are pictures for the corresponding lattices and the symmetry groups. And then in each case, we will be interested eventually in orbifold taking quotient by the symmetry group. So let's just do this for the elliptic curve. You take quotient of E by roots of by a group. In each case, what you get, you will get just a projective line. There will be just one function, one basic function, elliptic function, which is invariant under this group, and all others will be just rational function of that one. So this means that you get P1, but it's more convenient to think this as orbifolded P1, and our orbifold points will correspond to fixed points of this section of the roots of unity. And you will have, depending on the cases, you can have either 4 fixed points or 3 fixed points in these cases. And the numbers which I put here are the, if you think the orbifolds, you're talking about local symmetry around each orbifold points. So here it's a local symmetry around each fixed point. And so in this case, for example, when you have quotient of elliptic curve by Z2 symmetry, you have 4 fixed points which are half periods, and each has stabilizer just the full group Z2, and so these are numbers 2, 2, 2, 2 in this case. In this case, you have 3 fixed points actually. Each has stabilizer Z3, so I put the orders of the stabilizers of fixed points here, and in this case you get these numbers, and so this is for the most complicated case. And now if you think about affine Dynkin diagrams like this, all of these have central node, and then you can start counting how many nodes on each legs you have, including the central node. So in this case, you have central node, so two nodes on each leg, and in this case, you get yes. For E6, you got 3, 3, 3, and similar to you got 4, 4, 2 in this case, and 6, 3, T for E8. Okay, so that's this suggests that there might be some correspondence. And if time permits, I will mention actually more conceptual link, deeper link between these elliptic curves and these Dynkin diagrams. Okay. Right. So this is just a picture to illustrate what I said. 4 fixed points in this case. The elliptic function, which is invariant under q goes to minus q, is the p function, and so this plays the role of coordinate on this p1, and the 4 fixed points are mapped to these values of p function in these 4 half periods, and stabilizers are 2, 2, 2, 2, so different color just for convenience. And here is what happens just as an example for m equals 6. The 0 is fixed under the full group, so this yellow point has stabilizer Z6. There is another, so what the red points represent actually a special orbit. So there are special orbits for the section of Z6. One special orbit I already mentioned, this is 0. 2 red points represent a special orbit of length 2. So each of the points has stabilizer Z3. So I put Z3 here. And the blue, the red, green points, 3 green points, which are half periods, they represent the orbit of for the 3, another special orbit. And so stabilizer is Z2. So 3 numbers 6, 3, 2 corresponds to 3 special orbits and the stabilizers. Okay, so now we want to consider spherical periodic algebra. So how many deformation parameters you have? So if you look at this orbifold singularities locally because locally it looks like C2, but quotient not by the full ZM, but only by stabilizer. So you get these locally singularities look like these cyclic singularities with corresponding MI, and the fixed points, the special orbits. And each of them, remember that baby example I discussed before, each of them has m-1 parameter of deformation, so you might expect as many deformation parameters altogether. You need to sum up these numbers over 3 orbifold points. And so these are these numbers. And so if you sum mi-1, here you get sum of 1 plus 1 plus 1 plus 1. So 4 parameters of deformation you can expect. And here 2 plus 2 plus 2, 6. And here 7 and 8. And this matches the rank of this the algebras. Okay, so and that's exactly what happens. So you get as many deformation parameters as written here. And now, because you have just P and Q, it's just 1 degree of freedom for your integrable system. You get just 1 Hamiltonian. So integrable system is given just by 1 Hamiltonian, which will be polynomial of order m, degree m. The coefficients will be elliptic functions of Q, and they also depend on those extra parameters of deformation. Here are 2 examples which are easy to write down. For m equals 2, this is a rather familiar looking Hamiltonian. You can recognize this as sometimes it's called, this is rank 1 version of BCN Hamiltonian of Calogero Moser type. So 4 parameters of deformation appear here. Traditionally, you write full squares. It's just tradition. And so you have 4 parameters of deformation, and these are elliptic function shifted by half periods. And if m is 3, you get cubic Hamiltonian of this form. So you have 3 terms appearing in front of P and 3 terms appearing in the coefficient of degree 0. So 6 parameters here you get, and eta 1, eta 2 are those red points which we saw in the previous picture. Fixed points for the action of the group. And but the Hamiltonians get very complicated for m equals 4 and 6, so I will not write them down. Initially, we had the formula which for m equals 6, which takes about maybe 2 pages to write down. Now we have a more compact expression, but maybe I will have time to show it later. Okay, so now, so this is just one Hamiltonian, and of course, what you do, you consider level surfaces of Hamiltonian, and you would like to see elliptic curves appearing there. It doesn't happen like that. So of course you have foliation by levels of Hamiltonian, and dynamics happens on these level surfaces. But these surfaces have a rather high genus, m squared plus 1. So for example, when m is 6, you get a surface of genus 37. But so it doesn't look like integrable system maybe. But the point is that there is a symmetry, underlying symmetry, and you need to take a quotient by this symmetry group, and then very nicely actually what you get will be an elliptic curve. So you get elliptic fibration not on original phase space, but on the quotient by Zn on this orbifold. And indeed, you can show that the dynamics is linear along these elliptic curves. Okay, so this is nice. And now you can do this directly if you have formula for the Hamiltonian. And actually, for this Hamiltonian, the simplest one, quadratic, you can trace it down in the literature. First, I think there was a paper by Magnus in the 30s, 1930s, where he discusses actually questions of quantum systems, but you can extract from what he says that, for example, this one you can integrate classical dynamics for this one in elliptic functions. So this is not widely known, but it's a nice exercise. Okay, so but there is another. So one way is of doing that directly using the formula for Hamiltonian, but there is another way more useful, especially when you go to higher rank case, is to look at the Lux representation. And Lux representation exists for these systems, and the Lux matrix in this case will be of size m by m. Remember, m is 2, 3, 4, and 6. For m equals yes, so for m equals 2 is 2 by 2, and but it looks a bit complicated in general. So the structure is as follows: along the diagonal you have momentum with some roots of unity, and away from diagonal you have some complicated elliptic functions. I will show them on the next slide, but you don't have to read it. It's a bit complicated. So it's a combination of several terms. This function is rather well familiar in theory of elliptic integrable systems. It's a combination of Weierstrass sigma function like that, but there are several terms and there are certain ingredients, summation of fixed points, and the deformation parameters appear as a coefficient. So it's quite complicated, and so and then you would like having a Lux matrix. What you know is that you can show that the determinant of this, the characteristic polynomial of this Lux matrix remains constant under the evolution, time evolution. So this spectral curve, how it's called, doesn't change in time, and so you would like to calculate it. And this is for m equals 6 by 6 determinants, lots of elliptic functions. It doesn't seem easy, but there is actually a way to find this using some nice duality, which seems important. So these elliptic functions, which I just briefly showed in the previous slide, they have this interesting symmetry. So if you swap the roles of the, yes, I should have mentioned that there is extra variable there, alpha, which is a spectral parameter. So this is the best you can hope for having Lux representation with spectral parameter. This spectral parameter lives on the elliptic curve again, and so the spectral curve actually is a curve in this space So the alpha is it's you can think again of this as a cotangent bundle to your elliptic curve. Alpha is on the elliptic curve, k is in the tangent direction. Okay, so yes, and the duality, which is helpful here, is that if you swap the roles of your dynamical variable q and the spectral parameter, then these functions just you get minus, but you need to change L to minus L. But you also, importantly, you need to change these couplings to some dual couplings, which are rather complicated. Okay, so and then here's some formulas for this transformation from parameters to the dual parameters. When M is 2, this should be familiar to people who knows about this kind of BCN type Calogero Moser system. And so this is an evolution on the parameters in this case. For M equals 3, this evolution looks more complicated, something like that. And we have formulas for other cases and some interpretation, at least theoretic interpretation of these, but it's a bit complicated to explain now. So, but you have more than just this symmetry of these coefficients. From that, you can actually get some strange kind of duality at the level of Lax matrices. So what is written here is this duality at the level of Lax matrices. So here's my original Lax matrix and the expression. I would like to calculate determinant of that characteristic polynomial, and it turns out that you almost up to this some extra details. You essentially get the same answer as the characteristic polynomial of the dual matrix, where you, in the dual matrix, you swap the role of, you trade your PQ to K and alpha, and Q becomes spectral parameter. And you change the couplings to the dual couplings. And so these two matrices somehow match. And so roughly it means that your original Lax matrix is almost the same as Lax matrix in the dual, in the spectral variable. And if you change parameters. Oh. Okay. And from that, you can see rather easily that actually the answer for your characteristic polynomial will be just the difference of two Hamiltonians, one your original Hamiltonian in PQ, and another one is the dual one in terms of the spectral variable. Okay, so if you fix, remember I told you that the spectral, this polynomial should remain constant under the motion. And that's indeed obvious now because this is a Hamiltonian, it remains constant. So under the evolution, if you fix the value of Hamiltonian to some number z, then the spectral curve is just the level set of this dual Hamiltonian in the spectral variables. Okay, so you get another fibration here on the spectral side by these curves, similar looking curves, but with different Hamiltonian, different couplings. And again, you get the same result that if you take quotient by ZM, you get elliptic fibration. And hence, what we have, it's an interesting kind of picture. We have actually two fibrations over the same base Z. So you can either fix the value of what I did before on the previous slide. I fixed the value of H in terms of PQ. Then you get one fibration, which I call them check. And another one, if you fix the value of H check, then you get the level surfaces of my original Hamiltonian in the original space. And that's another fibration. And what you can show, which is not quite obvious, is that you have duality of fibrations in the sense that the fibers are isomorphic as elliptic curves. Although it's far from obvious because there are complicated transformation of the parameters in these elliptic curves, and these elliptic curves are actually of high order, as we will see later, and higher degree curves of geometric genus 1. So this is far from obvious, but nevertheless, that's the result. And you should probably think of that as kind of an instance of this. There is this SYZ mirror symmetry for Hitchin fibrations. Actually, there is you can interpret these vibrations as Hitchin vibrations for parabolic Hitchin systems. And so you can think of this phenomenon as mirror symmetry for this.
Are there any single fibers as well?
Yes, yes, there are singular fibers, yes. Yes, 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 that's that. Well, this is just isomorphism, right? So the J invariants will be the same on the open set and therefore the same globally, right? So that shows that at least as curves they're isomorphic, even if they're singular. Okay, and now to understand this vibration geometrically, you would like to work in invariant coordinates under this action of Zm. And it turns out that if you do that, then what you get are some nice elliptic pencils, which you can describe geometrically. And I'll give answers for m equals 3, 4, and 6, and then m equals 2 may be up to that. So the elliptic pencils which you get for m equals 3, 4, and 6 naturally sit in P2 on the projective plane. And the first case is rather natural. So what you need to do, you need to pick a triple of lines, intersecting lines in P2. And then you need to pick 3 points on each of the lines. So I think of lines as just linear forms, so equations given by a linear form in homogeneous coordinates x, y, w. And so what turns out is the following, right? Okay, so first of all, if you pick 9 points generically like this, there will be no other elliptic curve passing through these 9 points except the reducible one, which is the product of these 3 linear forms. But there is, if you impose just one constraint of these 9 points, roughly saying that the sum should equal to 0, then there will be a pencil, exactly one-dimensional family of cubics of these 9 points. And so the pencil, the elliptic vibration I discussed before for the integrable system here becomes, you can identify it with the elliptic vibration on this P2 by the members of this pencil. So you have one-dimensional family. So you just need to calculate one of these cubics, and then another one is the one which is a product of three lines, and then general cubic in this pencil looks like this, and so the pencil effectively depends on so parameters of deformation which determine the pencil are positions of these 9 points. There is also triple of lines, but triple of lines in projective line up to projective transformation, you can make it as you wish. So you might think that there are 9 parameters, but I told you there is one constraint, so only 8 parameters left. And then there is also a 2-dimensional group of projective transformation, which preserves this triple of lines. And so you get 6 parameters. Remember, it's E6 case, so 6 is what we expect. And then this formula actually allows you to express this z in terms of as a rational function of x, y, and w. And then if you go to affine coordinates x and w, this gives you actually expression for your Hamiltonian z in terms of the variable. So that's another way of obtaining formulas for the Hamiltonians geometric. Okay, so that's the answer in this case. When m is 4, the modification looks as follows. So now again a triple of lines. Remember the numbers we had sometime before in this case were 4, 4, 2. And so it means that you need to pick 4 points on that line, 4 points on that line, and 2 double points on this line. Now the curves you're looking for would be not cubics, but quartics. And quartics, which, so this cross here indicates that so first they should pass through all these 8 points here, but also they should have ordinary double points at these 2 points. Okay, so quartics with 2 double points it is well known that they have geometric genus 1. So these are automatically elliptic curves, and all you need to do is the following calculation. You need to find the equation for one curve passing through these 10 points like this, and then another curve in this pencil will be just reducible, again, reducible curve product of two lines, and then this line, because you need double points, you need to take a square of that. So that's a quartic, reducible quartic, and so similar to what we had before, you get a pencil in a similar form. Here, just L2 will be squared. Okay, so that's the answer for m equals 4. And for m equals 6, what you get is, again, you could guess by now. Again, 3 lines. You need 6 points on one line, 3 double points, and 2 triple ordinary points on this line. Now you're looking for curves of degree 6, so sextics of geometric genus 1. And the genus will be 1 automatically if they pass through the points as written here. So P7, P8, P9 should be double points, and P10, P11 should be triple points. And if you think about that again, you can figure out that this configuration effectively depends on 8 parameters, and these 8 parameters match precisely to deformation parameters of the geometric algebra, but also you can also see that the Seiberg Witten differential, which you get for this elliptic fibration, will have, well, in this case, 18 simple poles, and the residues of the Seiberg Witten differential at these poles will be, these 8 parameters will describe the residues of Seiberg Witten differential. These are mass parameters of theory. So that's just a nice kind of correspondence between geometry, deformations, and physics. For m equals 2, the answer is more natural to be viewed on the weighted projective plane. So here y has weight 2. This weighted projective plane has one conic singularity, and you take 4 lines passing through this conic singularity, and then on each of the lines you pick 2 points. And the curve you're looking for should be of degree 4, but in the weighted homogeneous sense. So it will be quadratic in y, and degree 4 in x and w. And so you get a pencil of that kind, which depends on 4 parameters. In addition, there is extra parameter here, which is a double ratio of these 4 lines, which is that modular parameter corresponds to the modular parameter tau, which you have in this case, because elliptic curve, underlying elliptic curve, remember, is allowed to have arbitrary modular parameter tau. Okay, so that's the geometric way of giving the answer for these elliptic vibrations. And I should say that for these rank 1 theories, these elliptic vibrations in different form were known before. For higher rank, it wasn't the case, but for this case, they were known before in a Weierstrass form, which is more complicated. And in particular, Seiberg Witten differential, I remember, for example, for if I remember correctly, for example, for Minahan-Meshansky E8 theory, Seiberg Witten differential, if you write this pencil in elliptic form, it had 240 simple poles. And here we have just 18. So it seems much more symmetric way of obtaining this vibration. So rather compact, and formulas look much more compact, symmetric. Okay, so let's now talk. I have some time to discuss quantization of these spectral curves. And this is, again, these examples I like because they give you some kind of vivid instances of various things. So quantum spectral curves, you can observe here. Hitchin vibrations, mirror symmetry for Hitchin vibrations I've mentioned before. Also, you can see here instances of this geometric Langlands duality as well. And So these are nice kind of examples where you can just see this with your bare hands. Okay, so let me explain how one quantizes this spectral curve. So these are algebraic curves, and by quantizing, you expect to get some ordinary differential equation. And there is no general recipe. There are different approaches how to quantize curves, and topological recursion, for example, is one approach. But here we can do it naturally because remember, this was Hamiltonian. At least, well, okay, in the original variables P and Q, this was Hamiltonian of the. It's not immediately clear how to quantize the spectral curve, but the dual one, it meets a natural quantization because this was classical Hamiltonian, and the theory of this integrable system allows you to construct a quantum Hamiltonian. It will be differential operator for the M. I put Planck constant to 1. So there is a natural quantization of that. And because this Hamiltonian at the classical level was exactly the same formula, just replacing parameters by dual parameters, it is natural to therefore to quantize spectral curve in a similar fashion. Just take the quantum Hamiltonian and replace the variables Q with alpha and replace parameters with the dual parameters. And so in particular, this is the original Hamiltonian after quantization. This G squared becomes G plus 1. A bit more complicated, but third order operator you get in this case, and for m equals 4 and 6, you get fairly complicated differential operators of order 4 and 6, and then you can put this together as follows. So this is my quantum Hamiltonian, and instead of the spectral the foliation by level surfaces at the quantum level, what you do, you consider this eigenvalue problem. So that is eigenvalue. So you get this, if you wish, a pencil of ODEs, and the dual one looks similar, and but in the spectral variable, and then you can put them together like this. So this is kind of so this is quantum spectral curve, in the sense that if you fix the value of your quantum Hamiltonian, you get the second pencil of ODEs, and this is parallel. This formula looks parallel to the formula we had for the remember, for the classical spectral curves, they are written as difference of Hamiltonians, H check minus H, and we have it here. And so you can find solution to this PDE by taking the product of eigenfunctions for these two problems. So you have one parametric family of solutions to this. Okay, so that's the. And then if you think of this, there is, as I mentioned, there is interpretation of this as Hitchin. As Hitchin vibrations and Hitchin systems, and this is then a quantization of Hitchin Hamiltonian, and these ODEs actually have very special properties in terms of their monodromy, and I don't have time to explain this in detail, but I will just say that the monodromy. So here you can see appearance of those, again, those quivers of type D4, E7, E67, E8, because the monodromy for these Fuchsian ODEs turns out to be rather special, and you can identify it with, let me see if I have it written somewhere. No, okay. Right, okay, so let me just say it like this. So you can identify this with Hitchin, this vibration with Hitchin vibration for a parabolic Hitchin system on the punctured Riemann sphere. And then you have, according to non-abelian Hodge correspondence, you have Higgs modular space, you have the RAM modular space, and Betty modular space. And I started with fibration here, which was elliptic fibration. This corresponds to just Higgs modular space, or Delbour picture. But then on the RAM side, what I obtained as quantization, actually, you can see that this quantum spectral curve, they naturally live inside this de Rham phase space. So what you get is it, go back. And the Betty side of this story, or monodromy of this local system, will be actually multiplicative Quiver varieties for this of this type D4, E7, E6, E7, E8. All right, but what we get as a result here is that it matches this philosophy going back to Nekrasov, Rossley, Shatashvili, and Gayota, which tells you that quantizing spectral curves of a huge system should give you a Lagrangian variety of 4 pairs inside the RAM space. For complete curves, for GLN, it has been established already, but here we're dealing with the case of parabolic systems, weakly parabolic systems. So there is no general result in this case, and so this is just an illustration in this case. Okay, so I think I'll stop here. Thank you very much.
Okay, any questions?
Well, if you consider Calogero Moser type systems for any root systems, yes. And in this case, where all the system have Dunkel operators. How Dunkel operators can be fit in this picture? Because really Dunkel stuff can be generalized not for integrable systems on quantum spaces. That means quantization, not this about quantization in the sense of Gromov-Witten.
Here, actually, there are Dunkel operators here in this story.
Of course, well, it should be, but Dunkel operators is operators of order 1 instead of Hamiltonians.
Yes.
And Hamiltonians is a really simple combination, simple function of Dunkel.
Well, in this case, it's not so simple, unfortunately, because the Dunkel operators, natural Dunkel operators, were constructed for this in this generality for complex crystallography groups by Etingof and Ma, and they depend on spectral variables. So in this case, just one variable, and that alpha actually will appear in the Dunkel operator. So Dunkel operators will be of order 1. The coefficients will not be purely elliptic, but kind of certain quasi-periodic functions, ratio of theta functions, and they will depend on in addition to being differential operator in Q of order 1, there will be a reflection part with the group, but the coefficient in front will depend on the spectral parameter alpha. They will commute for fixed value of alpha, but to get the Hamiltonian, you need to take certain combination of them, and then which will depend on this spectral parameter. So it's not so easy actually to get this. That's the problem here, to get the expression for, where is H? I had before. So to get the, I need to go backwards, sorry. So to get the expression for these Hamiltonians, it's fairly straightforward for m equals 2, but not so easy. Yeah, that's not so easy for m3. It's possible, but not easy already. And for m equals 4 and 6, it's very difficult. So we used really kind of different way of finding this H, because we know that it's the only global section. We're looking for global sections, and we find that up to constant additive constant, the only global section has this form. So yes, there are Dunkel operators. H can be constructed by taking complicated expression in terms of this Dunkel operator, and then letting spectral parameter go into zero. So that's a more complicated story than the usual one.
Yes. And the last question is, you consider only crystallographic complex reflection groups, for example, where is so in your case, this is just extension of symmetric group by cyclic group of order 2, 4, 6. But crystallographic groups exist for any extension of symmetric general linear group by symmetric group by cyclic group.
They will be finite so-called complex reflection groups, right? Finite complex reflection groups.
Yes, and they have a nice theory of Dunkel operators.
Yes.
But can you extend this result of your classification for E algebra for E groups higher order? For E10, or for E9.
So in this setup, in this approach, these are ruled out because we want them to preserve lattice. If you in this setup you want them to act on abelian variety, then you cannot have, for example, symmetry for the phi. So that's why we have this restriction. It's crystallographic restriction, yes. But finite groups, as far as I know, nevertheless also appeared in these SQFTs as well. They have relevance to SQFTs indeed, but not in this story. Yes, thank you.
Okay, thank you. So let's just thank the speaker again.